Xavier. Thanks for the organizer for your invitation. So we have with Patrick the nice position to be between you and your lunch. So we will try to make it as short as possible, hoping that you will be interested. So when I first been asked by Xavier to prepare a presentation set and in order to address the critical interdependence between of chips and connectivity, I found that relating the 6G journey could be a nice approach in order to make it. Let's start with 6G. What the crowdsourced crystal ball tell us. So when 3 years ago we published within NOKIA Bell Labs our vision of 6G in a blog, we did an online poll and asked mainly 3 questions. So the first question was, what will be the defining new application for 6G era? So we had quite balanced answers, and many of them were about immersive experience, digital physical fusion, etc. So this is all the expectations that we will have in this new world. The second question was about the new technologies that will be implemented in 6G. Here we have really a dominating answer, which is that for 6G we will need to implement artificial intelligence-based networking. The other answers were also very important because it unleashed some new architecture, like the cloud-native architecture that you will see is very important at least in our vision. For the last question was about the important KPI for 6G. Here we had also, balanced answers, and it appears that security and trust is really a concern. It was mentioned this morning by Jean-Luc in his presentation, and we see that all these answers could be summarized in three topics. The digital physical fusion, that this new network will be powered with artificial intelligence, and we need safety in quantum grade network. So what are the key defining technologies for 6G? So we have them 6 technologies for 6G. So this was built like a consensus between NOKIA and other industrials and academic. In particular, we built this consensus in the flagship program EXA-X that has now an EXA-X2 follow-up. So from this, while all these new technologies will require significant research, I will focus on 3 new technologies that requires chip disruption in order to resolve some critical issues associated to their design and fabrication. So the first one, the first new technologies that I will be defining will be on the architectural view of the network. So it is composed, in our view, it is composed of 4 pillars. The first one is you can see that the implementation of the network in 2030 will be like a multi-cloud interconnection over which the 6G communication and sensing capabilities will be implemented in a complete disaggregated way. With the, of course, the agility offered by cloud native design. So to allow this implementation, we will rely on an essential fabric. So the essential fabric will interconnect the multi-cloud between each other, and also all kind of access network. It is composed mainly of the new IP optical network, but also the standard optical network made of metro and core networks. In reality, the new 6G network will be a network of networks that need to coexist, and that has this coexistence will be also linked to different access networks like the data center network or the CSP networks. We have also the private wireless network. You have heard more and more about enterprise applications. And we have, of course, the non-terrestrial access network. So this kind of network need really to be frictionless, need to have frictionless operation. Artificial intelligence will be key in order to ensure the necessary automation and orchestration. So you see that the difficulty will be to make sure that all this network could coexist between each other with different stakeholders, CSPs, industrials, etc. So the second new technology that we think will be key for 6G is about new spectrum. So the terahertz, for example, will be offering a huge opportunity for 6G because of the large spectrum bandwidth available at this frequency that could allow 6G to increase the data capacity and also to implement, as mentioned this morning, the radio sensing and localization. So we will need semiconductor development and innovation in this area, in particular to improve the performance, to lower the power consumption, but also to increase the density of integration of digital analog mixed signal, RFICs, that constitute the 6G radio. So I will give an example about this sub-terahertz application. So you can see here that one of the critical aspects in 6G, in addition to the digital technologies that you heard about, digital semiconductor that rely on the most advanced CMOS node FinFET, 5 nanometer, now 3 nanometer. We will have also the analog component that will appear more and more critical for this application, simply because analog component did not follow Moore's law, so it's very complex to, let's say, have a dedicated team. You need to have dedicated team because it has to have dedicated designs because of the difficulties to scale DC power size, etc. So we have seen recently that there was a strong consolidation in this area, which make it difficult to build some roadmaps with partners. There is also a new disruption that needs to appear in this area, which is the use of 3.5 technologies that enables higher frequency operation, low noise, and high output power. So you can see it in the figure where we represented the saturated power versus the frequency. And if you can see here at the sub-terahertz area, the indium phosphide is appearing as one of the semiconductors that could answer to many of our specifications in this frequency range. So most probably we will have some sort of wafer scale integration of these 3.5 technologies with CMOS, because CMOS has still the monopoly in terms of scaling, I mean the density and also the low cost. Here we give you two examples that were achieved internally on, let's say, D-band transceivers achieved, realized in 2022 in Bell Labs. Here, for example, is first 256 element D-band array. So the criticity here is about power consumption and also density of integration. The next slide is about the final new technology is about how to solve the extreme connectivity equation. So we know that processors will be used everywhere in cars, in factories. They are really now the basic of many things. So they need to have critical aspect in terms of power, scalability, and flexibility. I will not enter into the detail, but we are speaking about artificial intelligence, but in the future we will have dedicated accelerator IP, which means that it will be chips that need to fulfill this function. For example, for scalability, the system on chip that we are developing for 5G need to be adaptable for many networks. When you build a radio network, you need to be able to address a CSP customer, but also, let's say, a private customer. So the enabling technologies that I mentioned here are coming from roadmap program that with Patrick we were pleased collaborating called CORNECT CSP. So for CORNECT project, in CORNECT project we defined that memory technologies and architecture were key for 6G. It will be also important to develop digital building block. And as I mentioned in the previous slide, the analog mixed signal will be also very important. So let me now give you just the vision of NOKIA. We think that in order to unleash the potential of connectivity, you will need to have internally some disruptive chips. So this is what we are doing either in access, for example, with our PON line termination. It's a 25G PON, a Quillion DSP chip. I think you have heard that we have internally a ReefShark SoC for 5G, but also on the optical part, we have this FP5 IP router. And very recently, just 2 weeks ago, we announced the NOKIA Photonic Service Engine 6S that is able to address 1.2 terabytes per second on a single wavelength. So what is interesting here is the design of these chips is made in Europe. So this is quite interesting for us as ecosystem. So here is just this picture because I like it. I show it to you. It's like our internal iPhone in NOKIA. So just to summarize, and I think maybe open the discussion with Patrick later on and Xavier. We have been facing with the chip shortage that revealed that we have a fragile supply chain on semiconductors. In terms of long-term strategy, we believe that we need to work on our strength, both to build the digital infrastructure and the industry vertical, catalyzing research and innovating in microelectronics and photonics, as shown in the previous slide, is really important for the connectivity ecosystem, especially for NOKIA. Eventually build a full strategic value chain. In Europe, there are many discussions in other society. we think that controlling a specific part of it, in particular the competitive parts, like the chips design capabilities to allow us as a company to, and one of the main actors, to lower the cost of our product is really important. Last but not least, growing the talent pipeline and skills for us is really important, and create some mutual dependencies between different regions. And for that, I see that the cluster Eureka is playing a really foundational role. Thank you.
So, thanks a lot, Mohand. Yes, questions?
Very exciting future, really. Do you foresee any new type for 6G? Do you foresee any new type of network traffic going beyond speech, audio, streaming, etc., i.e. what we are having today?
Yes. I think, yes. Thank you for your question. Jean-Luc this morning already started to elaborate on this question. In fact, the capabilities that this new network will be offering is really huge. And we think that we don't see for the moment all the application coming. So we are defining in the EXA-X program, for example, different use cases. I invite you to read those use cases that we are developing, but the capacity in terms of verticals, autonomous driving, but also the immersive sensing will be really opening very huge opportunities. Yes. So the answer is yes.
Okay, thank you.
It's just sort of following on. What's immersive sensing?
So
how do you see that, or feel that, or touch that, or smell that?
I think your neighbor will be able more to answer to this question than me, because she is a specialist in radio wireless. Extreme sensing, as mentioned this morning, it's to be able really to react of all the environmental information that we can capture. I can give you an example. For example, for submarine network, we have the capacity today to have some dedicated fiber in order to sense under the sea and be able, for example, to to detect some earthquake or tsunamis. So this is, and we can do it in real time. So you can imagine that you can sense also the environment, and all the information that you can get, you can use them to build some models and anticipate some behavior in the future.